Quantum entanglement has a reputation problem. It gets dragged into pseudoscience, wrapped in mysticism, used to sell dubious wellness products and explain paranormal phenomena that don't exist. But strip away the nonsense, and what's left is genuinely strange. Strange enough that Einstein called it spooky action at a distance. Strange enough that physicists spent decades trying to prove it couldn't be real. And strange enough that we're now building technologies around it that would have seemed like science fiction a generation ago. So here's what entanglement actually is. When two particles interact in the right way, they can become correlated in a manner that has no classical equivalent. Measure one particle, and instantly, not approximately instantly, but genuinely instantly, you know something definite about the other, even if it's light years away. The particles don't have individual quantum states anymore. They share one combined state. They've lost their quantum independence. This happens through a specific process. Take a high-energy photon, send it through a special crystal, and occasionally it splits into two lower-energy photons. Energy and momentum conservation create correlations between these photons. They emerge entangled in their polarization states. If you measure one and find it vertically polarized, the other is immediately horizontal. Not because they agreed on this in advance, but because they exist in a superposition of both vertical until you measure. And that's the conceptual shift that matters. These aren't two separate photons carrying hidden instructions. The mathematical description of the pair doesn't factor into two independent pieces. They're one quantum system occupying two locations. Entanglement is defined precisely by this mathematical non-factorizability. The whole is not just greater than the sum of its parts. The parts don't have independent quantum existence. Now, you might think particles must have definite properties all along, and we just don't know what they are. Maybe each photon has a predetermined polarization from birth, like tearing a photograph in half. You see your piece, I see mine. Perfect correlation, nothing mysterious. Einstein thought something like this must be true, because the alternative seemed to require faster-than-light influence, which violated relativity. In 1964, John Bell proved Einstein wrong, not with experiments, but with mathematics. Bell showed that if particles had predetermined properties, even hidden ones we couldn't directly observe, there would be limits on how strong their correlations could be across different measurement combinations. He derived an inequality that any theory with local hidden variables must satisfy. Then he showed quantum mechanics violates this inequality. Nature produces correlations that are too strong to explain with any pre-existing local properties. For decades, this was theoretical. Then experiments started testing it, measuring entangled particles at different angles, checking whether Bell's inequality was violated. Experiments in the 70s and 80s found violations, but there were loopholes. Maybe detectors were too inefficient, catching only special photons that weren't representative. Maybe measurement choices weren't made fast enough to prevent hidden signals between detectors. In 2015, 3 independent experiments finally closed all major loopholes simultaneously. They used fast random number generators to choose measurement settings at the last moment, high-efficiency detectors that caught nearly every particle, and large enough separations that light couldn't travel between detectors during the measurement. All 3 experiments violated Bell's inequality, exactly as quantum mechanics predicted. The 2022 Nobel Prize in Physics went to the researchers who pioneered these tests. What does this mean? It means local hidden variables don't exist. Particles genuinely don't have definite properties before measurement, or reality is non-local in a deep way, or both. You can't have your classical cake and eat relativistic locality too. Something has to give. But here's the twist that confuses everyone. This doesn't let you communicate faster than light. You can't use entanglement to send messages. When you measure your particle, you get a random result. The person measuring the other particle also gets a random result. The correlation only becomes visible when you compare results later through normal communication. From either person's perspective alone, their measurements look completely uncorrelated and random. The quantum connection is real, but it can't transmit information. There's a theorem that proves this, the no communication theorem. The local statistics of measurements on one particle are independent of what measurements were performed on the other. Only when you compare notes do you see the correlation. This means entanglement doesn't violate causality, doesn't create time travel paradoxes, and doesn't enable telepathy, no matter how much science fiction writers wish it did. This also means entanglement is useless for all the mystical things people claim. It doesn't connect consciousness. It doesn't explain psychic phenomena. Your brain is a hot, wet, noisy biological system where any quantum coherence decoheres in femtoseconds. There's no mechanism for maintaining entangled states relevant to cognition, and even if there were, the no communication theorem says it wouldn't let minds communicate anyway. What makes entanglement so fragile? Decoherence. Any interaction with the environment leaks information about the quantum state into that environment, destroying superpositions and entanglement. A photon scatters off a stray air molecule. An ion absorbs a thermal photon. A superconducting qubit couples to electromagnetic noise. Each interaction is effectively a measurement that collapses the quantum state into something classical. The timescale depends on how strongly the system couples to its environment and how big the superposition is. A single photon in good optical fiber can maintain coherence for milliseconds. The same photon in room temperature air decoheres in nanoseconds. A dust particle would decohere essentially instantaneously. This is why we don't see quantum superpositions in everyday objects. Not because quantum mechanics stops applying at large scales, but because decoherence is too fast. Despite this fragility, researchers have gotten remarkably good at creating and manipulating entanglement. The most common method uses spontaneous parametric down conversion in nonlinear crystals. Send a laser through the crystal, and occasionally a photon splits into an entangled pair. The efficiency is low. About 1 in a billion photons converts. But with bright lasers and sensitive detectors, you can reliably produce entangled pairs. For trapped ions, you use laser pulses to manipulate internal energy states and couple them through the ion's shared motion in an electromagnetic trap. For superconducting qubits, you couple circuits through shared electromagnetic fields and drive them with microwave pulses. Each system has advantages. Trapped ions offer the highest fidelity and longest coherence times. Superconducting qubits offer the best scalability for building large quantum computers. And quantum computing is where entanglement becomes technologically crucial. A quantum computer with 50 qubits can be in a superposition of over a quadrillion states simultaneously. Quantum algorithms exploit this by using entanglement to create interference patterns that amplify correct answers while canceling wrong ones. Without entanglement, quantum computers would offer no advantage over classical computers with random number generators. Shor's algorithm for factoring large numbers is the famous example. Factoring is believed to be hard classically. No efficient algorithm is known, but Shor's algorithm can do it exponentially faster by using quantum Fourier transforms on entangled qubits. This threatens RSA encryption, which is why post-quantum cryptography is being urgently developed. A large-scale quantum computer running Shor's algorithm could break much of current internet security. We're not there yet. Current quantum computers are noisy, intermediate-scale devices that can perform impressive demonstrations, but aren't yet practical for most applications. They have dozens to hundreds of qubits and can run hundreds to thousands of quantum gates before decoherence destroys the computation. Useful algorithms need millions of gates, which requires quantum error correction, encoding each logical qubit in many physical qubits to detect and correct errors. The overhead is substantial, and we're still working toward it. But quantum cryptography, using entanglement for secure communication, is already practical. The protocol works by using quantum states to distribute encryption keys. Any eavesdropper trying to intercept the quantum channel necessarily disturbs it in a detectable way. This isn't security based on computational hardness like RSA. It's security based on the laws of physics. You can't extract information from quantum states without disturbing them. Commercial quantum key distribution systems are operating now over fiber optic networks spanning hundreds of kilometers. China has built a nationwide quantum communication network. Satellites are distributing entangled photons globally. The technology has moved from laboratory curiosity to deployed infrastructure. What does all this tell us about reality? That depends on which interpretation of quantum mechanics you favor. And there's no experimental consensus. The Copenhagen interpretation says particles don't have properties until measured, and measurement collapses the wave function. Many worlds says all measurement outcomes happen in different branches of the universal wave function, with decoherence making branches independent. Pilot wave theory says particles always have definite positions, guided by a non-local wave. Relational interpretation says quantum states are relative to observers, not absolute. These interpretations make identical predictions for current experiments. They differ in what they claim exists and how they explain why experiments produce the results they do. Bell's theorem rules out local hidden variables, but doesn't favor any particular interpretation. You can have non-local realism, non-realism, branching universes, or relational states. All are consistent with observed violations of Bell inequalities. The research continues on multiple fronts. Experimentalists are creating entanglement with increasingly massive objects, molecules with thousands of atoms, mechanical oscillators, visible to the naked eye. They're testing quantum mechanics at larger scales, exploring connections between entanglement and gravity, and building better quantum computers and communication networks. Theorists are investigating whether entanglement is fundamental to space-time geometry, how it spreads through many body systems, and what it tells us about quantum phases of matter. None of this requires mysticism. Entanglement is precisely defined, mathematically rigorous, and experimentally verified to extraordinary precision. It's strange, yes. It forces us to reconsider basic assumptions about locality and reality. But it's the strangeness of nature behaving according to rules different from our everyday intuitions, not the strangeness of magic or pseudoscience. The practical applications are real and growing. Quantum key distribution provides provable security. Quantum computers will eventually solve certain problems exponentially faster than classical computers. Quantum. Sensors using entanglement achieve measurement precision beyond classical limits. These technologies work because entanglement is real, controllable, and useful, not because it's mysterious or supernatural. What we're witnessing is the transition of quantum mechanics from foundational physics to engineering discipline. The conceptual puzzles that troubled Einstein and Bohr are now the basis for patents and products. Entanglement, once the most troubling prediction of quantum theory, is becoming a resource that engineers manipulate routinely to build technologies impossible with classical physics. But the foundational questions remain. We still don't know what quantum mechanics is telling us about the ultimate nature of reality. We don't know how to reconcile it fully with general relativity. We don't know if there's a deeper theory underneath that makes quantum mechanics less strange, or if the strangeness is fundamental. These questions drive ongoing research alongside the technological applications. So when you hear about quantum entanglement, remember, it's not about consciousness or spirituality. It's about correlations that are stronger than classical physics allows, measured in laboratories with exquisite precision, and harnessed for technologies that are beginning to reshape computation, communication, and sensing. The real physics is strange enough without embellishment. Respect for what entanglement actually is means resisting the temptation to use it to explain everything mysterious. Nature is showing us something deep about interconnectedness and correlation, and we're still learning what it means. Thanks for listening. If you want the deeper version of this, check out the PM script where we spend 2 hours going through all the details. Either way, reality is weirder and more interesting than most fiction gives it credit for.